Hey there, and welcome to this explainer. So what if I told you that a machine could predict the future using literally nothing but probability? Really think about it. Every single day, your email inbox performs this seemingly impossible magic trick. It looks at an incoming message and instantly knows with mathematical certainty whether it's spam or not. How on earth does it do that? Well, today, we're going to unpack exactly how that magic trick works. We're taking a journey from absolute zero to machine learning mastery by exploring the naive Bayes algorithm. It is honestly one of the oldest, simplest, and most surprisingly powerful algorithms in the entire world of machine learning. Here's our roadmap for today. We're going to cover 1. The magic of prediction, 2. Bayes' theorem explained, 3. How the algorithm works, 4. Strengths and weaknesses, 5. Coding naive Bayes in Python, and finally 6. Real-world machine learning. Let's get right to it. Section 1. The magic of prediction. Now, you might be wondering, how does your email provider instantly know what's a genuine message from your boss and what's a scam trying to steal your password? The machine doesn't actually read the email the way you or I do, not at all. Instead, it relies on an incredibly robust, probability-based algorithm that acts like a massive filter. And this algorithm powers not just your spam folders, but huge medical diagnosis systems and sentiment analysis tools worldwide. The craziest part? It's entirely based on the simple concept of weighing clues. Okay, section 2, Bayes' theorem explained. So here is the absolute foundation of our algorithm, Bayes' theorem. I know, it looks like alphabet soup right now, but stay with me. This is literally one of the most important formulas in statistics. Let's just translate it into our detective work. Imagine you're trying to crack a case. That's our class, or the ultimate decision we want to make, like, is this spam? The capital A in this formula represents that class. The capital B represents our clues, or what data scientists call features, like seeing the words free or winner in an email. What this formula actually does is calculate the posterior probability. That's just a fancy way of saying the chance that our email is spam given the clues we just found. It does this by multiplying the likelihood of finding those clues in known spam by the general prior probability of getting a spam email in the first place. It's just weighing the clues to crack the case. That's it. Now, what's really interesting here is the word naive. Why is this brilliant mathematical theorem famously called the naive Bayes algorithm? Well, it's because it makes one incredibly strong, very bold assumption. It assumes that all your input features, all your clues, are completely independent of each other. Basically, it assumes that seeing the word free in an email has absolutely no relationship whatsoever to seeing the word money right next to it. So the naive assumption states that features act completely alone. But hold on, we know reality doesn't work like that. In the real world, words like free and money almost always travel together. Features influence each other, so the algorithm is making a boldly incorrect assumption about reality. But here is the massive plot twist on machine learning. Despite totally ignoring reality, this naive assumption actually works brilliantly in practice. By just pretending the clues are independent, the math becomes incredibly fast and remarkably accurate anyway. No way, right? But it works. All right, section 3, how the algorithm works. It all happens in 4 really simple steps. Step 1, the algorithm calculates the prior probability of each class from your past training data. It's essentially asking, historically, what percentage of all my emails are spam? Step 2, it calculates the feature likelihoods. How often does the word winner show up in those spam emails? Step 3, for a brand new, unseen email, it takes that prior probability and multiplies it by the likelihoods of all the specific words it finds in this new message. And because of our naive assumption, we can just multiply these individual probabilities together in a big chain. Finally, step 4, it assigns the class with the highest resulting probability. The case is closed, the final ruling is made, and the email hits your spam folder. Just like ice cream, naive Bayes comes in different flavors depending on the exact type of data you're feeding it. If your data is continuous numbers, like temperature or sensor readings, you're going to use Gaussian naive Bayes. If you're dealing with counts, like, say, how many times a word appears in a document, you'd use multinomial naive Bayes. And if your data is strictly binary, meaning a feature is either present or absent, just a 1 or a 0, you'd reach for Bernoulli naive Bayes. You basically just pick the flavor that matches your evidence. Moving on to section 4, strengths and weaknesses. So why do data scientists absolutely love naive Bayes? A few key reasons. First, because of that super simple math of just multiplying independent probabilities, it is extremely fast. Second, it excels with high-dimensional data, like text documents that literally have thousands of unique words. And third, Unlike modern deep learning neural networks that need millions of examples to learn anything, naive Bayes performs wonderfully even when you only have a very small dataset to train it on. It's super efficient. However, there are for sure some trade-offs. As we discussed, that strong independence assumption rarely holds true in the real world, which makes the model pretty sensitive to highly correlated features. But the biggest headache? It's something called the zero frequency problem. Imagine our model has never ever seen the word crypto in a spam email before. The likelihood probability for crypto becomes a strict 0. And because we're multiplying everything together in step 3, well, multiplying anything by 0 turns the entire final probability to 0. Just one single unseen clue ruins the whole calculation. Keep that in mind because we're going to fix it in just a second. Section 5, Coding Naive Bayes in Python. Let's get our hands dirty. Let's look at a really small, concrete dataset. X represents our futures, our clues. Think of those numbers like measurements. Y represents our target class, the final answer. Notice how the lower numbers map to class 0 and the higher numbers map to class 1? We're going to split this tiny dataset into a training set to teach our model and a testing set to see if it actually learned the pattern. And this brilliantly illustrates how incredibly easy machine learning can be. 3 lines of code. Seriously, that's it. First, we declare our model. We're using Gaussian because our features are numerical measurements. Second, we use model.fit and hand it our training data. This is where the model does all the heavy lifting, calculating the priors and likelihoods behind the scenes. Finally, we use model.predict on our unseen test data. Boom, the model outputs its predictions. You've just trained and tested a machine learning algorithm. Now, of course, you can tune your model to make it even better using hyperparameters. Take a look at that second bullet point, alpha. Remember that super annoying zero frequency problem we talked about earlier, where an unseen word drops the whole probability to 0? Well, alpha applies something called Laplace Smoothing. It simply adds a tiny, tiny baseline number to all probabilities, ensuring that nothing ever mathematically hits absolute 0. It's this elegant, single parameter fix to the algorithm's biggest weakness. Just brilliant. And finally, section 6, real-world machine learning. Just take a look at this list. Spam detection at massive scales like Gmail and Yahoo. Sentiment analysis, reading thousands of customer reviews to figure out if they're positive or negative. Automatically categorizing breaking news articles by their topic. Predicting diseases based on patient symptoms. Identifying suspicious financial transactions. All of these incredibly complex real-world tasks are solved using this exact algorithm. Naive Bayes is the ultimate proof that sometimes the simplest approach, literally making one bold assumption and doing basic probability math, is actually the most powerful tool you can have in your toolkit. So we've successfully mastered naive Bayes, from the underlying probability theory all the way to real Python code. But our machine learning journey doesn't stop here. What if instead of using probability, a machine could predict a data point's future simply by looking at its closest neighbors? In our next lesson, part 8, we're going to explore exactly how the k nearest neighbors algorithm does just that. You absolutely won't want to miss how it uses pure similarity to make predictions. So keep learning, keep exploring, and I'll see you in the next explainer.